Hello, everyone. Thanks for coming. I hope you got your 100 gigabytes of free storage first, but don't worry about that. I'm really happy today to be able to introduce Dr. Sarah Pearce. She's going to be talking about the Square Kilometre Array project, which is a truly awe-inspiring thing that's being done largely in Australia. Sarah is the Deputy Director of Astronomy at CSIRO. And with no further ado, I'll let her go. Thank you.
What did the universe look like when the first galaxies formed?
What are gravitational waves? How does magnetism work throughout the universe?
Come si formano I pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうだったかな?
¿Estaba Einstein en lo correcto?
And for me, the most important is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answer to these big questions? We are building a time machine. We're looking at what our surroundings were like almost at their inception. The question is, how are we actually going to make this happen?
So, SKA is a radio telescope, as they mentioned. It's a Square Kilometre Array, but it's not actually square, and I'll show you some pictures of it later. But obviously, radio telescopes are just one part of the electromagnetic spectrum. Astronomers have got the whole electromagnetic spectrum covered, from the optical kind of telescopes that you would know about, both on Earth and like the Hubble Space Telescope in space, all the way through from gamma ray telescopes through infrared, microwave, and then to radio. So there are a number of radio telescopes around the world. They tend to be fairly large because radio waves are obviously longer wavelength, and you need a larger telescope than you do for, say, an optical telescope. And so for that reason, and because radio waves are transmitted through the atmosphere, so we can see radio sources in the universe pretty well, they're pretty much all on Earth, although there are a couple of radio telescopes in orbit, but that doesn't tend to be the most effective way of doing it. And Australia's got a long history in radio astronomy, and you'll hopefully all know about the Parkes Radio Telescope, which CSIRO runs. If you haven't seen the dish, I recommend you watch it before the 50th anniversary next year of the Apollo moon landings. Very fun and very exciting. So what do radio telescopes look for? Well, the most abundant element in the universe, as you know, is hydrogen. Hydrogen is a very simple element. One electron goes around one proton. But the proton has quantum spin in one direction, and the electron also has quantum spin. And when the electrons spin and the protons spin are in opposite directions, then what can happen is the spin flips, and what we call H1 lines are given off, hydrogen lines at 1420 megahertz, 21 centimeter radio. And we can see those with our radio telescopes. And so radio telescopes are really fantastic for watching what's happening with all the hydrogen in the universe, whether that's looking at what's happening in our galaxy, or whether it's looking at what's happening in the universe as a whole and how galaxies were formed and evolved. Hopefully, most of you here know about redshift. So the 21 centimeter line is given off in a rest frame at 21 centimeters, but if it's coming towards you, it'll be slightly blue shifted, so the wavelength will be slightly shorter. And if it's going away from you, as most of what's in the universe is, it will be red shifted, so the wavelength will be longer towards the red. And this allows us to see what has been happening since the Big Bang and to tell how far away things are. Because, of course, what is mostly causing redshift for us in the universe is the expansion of galaxies since the Big Bang. So with a radio telescope, by measuring what the wavelength is of the hydrogen 21 centimeter line, you can tell how far away and how fast the galaxies that you're looking at are. And similarly for things in our galaxy. So that picture there showed you briefly what difference that the Milky Way looks like when you look at it in the hydrogen line compared with how it looks in the optical line. Another key thing that we look for with radio telescopes are very fast spinning neutron stars called pulsars. And these neutron stars are about the size of Sydney, typically, maybe a bit smaller, 10 kilometers or so. But they weigh as much as our sun, and they spin often really fast. So they spin millisecond pulsars spin 1,000 times a second. And what they do is they give off signals that as they come past us, we can see. And we can see these short beeps of pulsars. And what do we watch those for? Well, in order to be able to see what's happening in the universe, they're great at telling us how gravity works in these really extreme conditions. The key thing for a radio telescope, though, is you need a balance of resolution and sensitivity. So resolution you get by spreading your radio telescope out. And how do we do that? Well, you can either build a giant radio telescope. And so the largest radio telescope in the world is the 500-meter square fast telescope in China, which was unveiled last year. Or you can use an interferometer. And so you can have smaller antennas, but spread them out. And the Square Kilometre Array will be spread out over a distance of up to 80 kilometers. So that gives you a high resolution. But you also need a high collecting area so that you get really good sensitivity, yeah? So that you can see things that are faint, or you can see the faint parts in bright and extended things. So we also need a reasonably large collecting area. So it's that balance, spread things out, have lots of them, but add them all up so you've got a reasonable collecting area. And so that's what the SKA and other telescopes will try to do. This is possibly the most famous interferometer in the world. It's the VLA in the US, and here's Jodie Foster listening to aliens with it from the film Contact. So that's a really important film for radio astronomers. And it's an interferometer, as you see. So, a number of dishes which we collect all the data from. So what are we looking for really with the SKA? Well, for the SKA in Australia in particular, what we're looking for is the signals from the very dawn of the universe, from when the first stars and galaxies really started to shine. So you have the Big Bang and inflation, things expand really quickly. But then over time, you get the conditions which allow the stars and galaxies to shine. But we have never been able to see this up to now. And in particular, you need low frequency radio telescopes in order to be able to see this, because it's such a long way back in the universe. And so the signal is really, really redshifted to those really long wavelengths. And what we think we'll be able to see is as things start to shine, there are kind of gaps in the ionization of the matter in the universe. And we'll be able to see, if you've seen the COBE pictures of the cosmic background microwave radiation, which were taken, probably a long time ago now, 10, 15 years ago, I guess. What we're looking for is a similar thing with what's called the epoch of reionization and the cosmic dawn. So when these first stars and galaxies started to shine. And it's really complicated to find, because what you have to be able to do is take away all the stuff in front of the epoch of reionization. So everything that's happened between kind of now and then, we need to be able to subtract from the image. And we need to make sure that we've done that really carefully with great calibration so that we can see the epoch of reionization just as it occurred not long after the Big Bang. That's not the only thing that we'll be looking for, though. So magnetic fields are a really important part of the universe, and something not well understood. So they're absolutely fundamental to how galaxies and stars form. But why did magnetic fields become the way they are now in the universe? And how do they work from a very small to a very large scale? Of course, dark matter and dark energy are also a really important part of what we're going to be looking for. So dark energy, in principle, makes up 69% of everything in the universe, but we don't know what it is. We can see what it's doing. It's making the acceleration of the universe, expansion of the universe accelerate. And this is the work that Professor Brian Schmidt got his Nobel Prize for. But we don't know what it is, and we don't even know what the dark matter is, 25% of the matter in the universe. So the SKA will help us either find out what these are or identify models that suggest perhaps we've got something wrong. And the other thing that we'll be able to do is look for new galaxies. So we will make with the SKA the biggest galaxy map that has ever been made of the universe, and a map in 3D, because you can, as I explained earlier, measure the redshift and you can tell how far away these galaxies are. So we'll be able to measure 1 billion galaxies with the full SKA over and map and do kind of what I like to think of as galaxy, sorry, I've forgotten the word. I have to move on. But you can look at lots of different galaxies and you can model how they evolve over time in a way that we can't with the relatively small number of radio galaxies we know about at the moment. Another key thing we'll be looking at is how planets form. Yeah, so how we get from those very small grains of matter to planet-sized objects. And SKA will be able to see rings forming around other suns. And then, of course, as somebody in the video mentioned, SETI, the search for extraterrestrial intelligence. So it's a bit of a long shot, but it's absolutely science. And SKA will be able to see things that are quieter than we have ever been able to see before, and be able to look and see if there are signals. We'll be able to see a mobile phone on the nearest star. So we'll be able to see if there are signals coming from elsewhere in the universe and detect those. And of course, we'll also be able to help with the work on gravitational waves. So you'll see gravitational waves are detected by the LIGO detector last year, won the Nobel Prize almost immediately after having been detected, and that absolutely fantastic signal that came from it, which was completely as predicted. I've rarely seen an experimental result that was so exactly as predicted. Well, I talked about pulsars earlier. Using radio telescopes, we can measure very, very precisely how the pulses from these pulsars vary. And that can help us to tell what's happening with the gravity situation that those pulsars are in. So we've got a double pulsar, for example, 2 pulsars spinning around each other, or a pulsar going around a black hole. And using those signals, we'll be able to also detect gravity waves. So like LIGO, but not quite the same model. And hopefully we can also build on that gravity wave model. Don't know what that is.
It's somebody watching remotely, but we're trying to.
Okay, trying. Yeah, sure. Okay, so there are thousands of astronomers worldwide preparing for the SKA. This is the SKA science book. It's actually 2 books because the printers couldn't make one big enough in just 1 book. And this was prepared by over 1,000 astronomers, and it's got more than 1,000 papers in it, setting out the massive range of science that the SKA will be able to do. So I'll just tell you a little bit about the kind of structure of the SKA in terms of governance. So it's an international project, yeah? And at the moment, although this has 10 members on it, we recently had 2 more members join, member countries, France and Portugal. So we now have 12 member countries who are all working together to build these telescopes. And it's really an absolutely international affair. I was lucky in the last few years to be part of Australia's negotiating team. There's going to be a treaty for the SKA, which is going to be signed very shortly. And it was a fantastic experience to sit in those international negotiations with governments and scientists represented equally around the table, and to negotiate how we're going to build this observatory, which is going to last hopefully at least 50 years. This is the headquarters of SKA. It's actually, the building's actually a little bit bigger now. It's going to be opened sometime in the next few months. And it's at Jodrell Bank, which is a very historic radio telescope, still in use though, outside Manchester in the UK. So that's the headquarters. I mentioned intergovernmental organisation negotiations. This was a picture taken in Italy. And these are the negotiating teams to set up the treaty for the SKA. It's called convention, in fact, to make the SKA an intergovernmental organisation like CERN or like ESA, or ESO, the European Southern Observatory, so that we've got that really strong governance basis for an observatory that can go on and build a telescope now, but also build future telescopes out for decades. We've obviously got masses of science teams. So we have a range of science working groups looking at everything from cosmology through to how stars form, through to SETI. And they meet regularly. This is, and they look at cosmic dawn, pulsars, and all the things that I've been talking about here. And so you could see very briefly, there was a picture of one of the science working group meetings. SKA will be built on 2 existing sites in South Africa and in Australia. And in South Africa, that's Meerkat that you can see in the distance there. So that's a 64-dish radio telescope, which has been built as a precursor to the SKA. And in fact, Meerkat was opened 3 or 4 months ago. And you may have seen fantastic images of the galactic center that the telescope took. So it's a really great telescope. And what will happen is SKA will be built among and around Meerkat, and Meerkat and SKA will eventually become one instrument. And then in Australia, we also have a couple of precursors. So this is ASCAP, the Australian Square Kilometre Array Pathfinder. And I will show you some more pictures of ASCAP later, but ASCAP is a 36 antenna interferometer in Western Australia at the Australian SKA site, which I'll talk a bit more about in detail in a bit. And there are other precursors too. So on top is a low energy telescope called HERA, which is being built by an international consortium led out of the US, being built in South Africa. And then on the bottom is a low energy telescope in Australia called the Murchison Wide Field Array. And you can see that these low frequency telescopes look quite different to what you might imagine as a standard telescope, because obviously their antennas are built to have the highest sensitivity at the frequencies that the telescope are looking at. And as I say, that's really low frequency for looking at things like the epoch of reionization. So what is SKA doing at the moment? So for the last few years, we've been in what's called pre-construction, but you might as well think of as the design phase. So there are 12 international consortia designing different parts of the telescope. And then when we come to construction, which will probably start in about 18 months' time, those different designs will all be merged together into one system. So the designs at the moment are at critical design review stage. About half of them have been through CDR and about half have still to go. And then we expect system critical design review. So to pull all those designs together, make sure that we have functioning designs for the 2 telescopes we're going to build. We expect that in the middle of next year. And Australia is playing key roles in a number of these consortia. For example, CSIRO leads the Infrastructure Australia Consortium, which is responsible for things like roads and buildings on sites. But we also play a really significant role in the Central Signal Processing Consortium, which is doing the digital signal processing. And I'll talk about that in a bit more detail later. But that's making a correlator and beamformer, so very high I/O digital signal processing, which will do the first pass processing of the data from the telescope. And so this has been going on for 3 years. Worldwide, people have been working on everything from, as I say, kind of the roads and the ditches that need to be dug, the foundations for the antennas and things, all the way through to the software that needs to be used in the science data processor at the supercomputing sites in both countries. And there is, in fact, hardware on the ground in both countries now. So there are test arrays, both in Australia, a low-frequency aperture array test at the Murchison Radio Observatory in WA. And there's also SKA antennas, first test SKA antennas being built in South Africa. And the SKA antennas are being built by our colleagues in China. And so they have a great deal of experience in radio astronomy antennas. And in fact, they built the antennas as well for ASCAP, for our telescope in Australia. So they're building them in China. They go in pieces, in containers, get shipped to South Africa, and then get put together by a Chinese crew on site. So it's been a very exciting 3 years doing the design and the early testing, but really things are starting to speed up now, and we will see construction. And so what are we going to build? So we're going to build 2 telescopes in the first phase of SKA, one in South Africa and one in Australia. So the South African telescope is in the Karoo, which is several hours from Cape Town. And the Australian telescope is in the Murchison Radio Astronomy Observatory, which is about 3.5 hours outside Geraldton in Western Australia. And why are they where they are? Well, because we need it to be quiet. And I'll talk a bit more about radio quiet in a minute. But these are images of what the two telescopes will be. So in Australia, the low frequency telescope, SKA low, and in South Africa, mid frequency telescope, SKA mid. And so SKA mid looks between 350 megahertz and 14 gigahertz, and it will be 200 dishes. So what it'll be is around 130 SKA dishes and the 64 Meerkat dishes that I talked about earlier, all operating as one radio telescope with a total collecting area of 33,000 square meters. And that will be spread out over 150 kilometers. And then SKA low in Australia looks between 50 and 350 megahertz, so that lower frequency range to look at what happened really a long time ago in the universe. But it's enormous. So it's 130,000 antennas. And the antennas, you might have seen pictures of them. They look kind of like Christmas trees, about this size. And they're made of aluminium, probably. So it's 130,000 antennas in 512 stations, so 256 antennas in each station, a kind of big, wide selection. And you can stand in the middle of a station and it feels like you're kind of surrounded by Daleks or something. It could be your Dalek army. And that's a total collecting area of 0.4 kilometers squared. So you can say, where's the square kilometer? We're not quite at that yet, but we hope that the telescopes, as we expand over time, will get to a square kilometer of collecting area. And that's what we've calculated is needed in order to look for 1 billion galaxies, which is what we talked about, which is what the aim was. And SK low will be spread out between 65 kilometers. So I talked about you need to be quiet. Yeah. So the signals that we're looking for are millions of billions times quieter than your mobile phone. So if you have your mobile phone near, then we can't hear them. And so how do you find it quiet? Well, these days, the only way you can make it quiet is to go somewhere where there are really no people. Yeah, and so that's why in South Africa, we're in the Karoo, and you can see the radio quietness, obviously, and you can see Western Australia as a whole is pretty radio quiet, right? But in particular, the area that we looked at areas to make sure that it was unlikely to be too attractive to mining companies, because clearly you can't have a mine kind of at the edge of your radio telescope. And an area that where we can work with the local people, so 3.5 hours outside Geraldton. So it's within striking distance of a city where you can get things, but it's nice and quiet. But the SKA low and SK mid that I talked about are not the kind of end vision for SKA. I mean, the idea in the end is to build a much bigger SKA, SKA2, which will hopefully be 1,000 dishes and 1 million antennas. Yeah, but that's some way away at the moment. And so first of all, we will build SKA1. And then hopefully we'll be able to raise the money to build this much larger telescope. So how does even SKA1, though, is a really significant leap for radio astronomy. So how does it compare? So SKA1 low, the nearest comparable radio telescope is LOFAR in the Netherlands. But SKA will be 8 times more sensitive than LOFAR, but importantly, it will have 135 times the survey speed. So really, you can look over the whole sky so much more quickly than we've ever been able to do in the past. And then SKA mid will have 60 times the survey speed of the Very Large Array. So that was the telescope with Jodie Foster that I showed you earlier. And that's the best of the radio telescopes at the moment, probably Meerkat aside. So 60 times the survey speed. So again, we'll be able to look and measure all those galaxies in a way that we've never been able to do before, because radio telescopes in the past have only been able to look at very small proportions of the sky at a time. So now I'm just going to talk briefly about Australia. So I mentioned Parkes. Australia's got a really long history in radio astronomy. You may not know, but some of the very, very first measurements ever taken in radio astronomy anywhere in the world were taken here in Sydney, just after the Second World War, when they adapted radar technology to look at the sky, and they used the sea as an interferometer to see what you could get when signals bounced off the sea. So Australia has been in radio astronomy since the very, very beginning of it as a science. And so we've got Parkes, of course, which has been going for more than 50 years now, played a fundamental role in the moon landing, not quite as in the dish, but not bad. We've also got the Australia Telescope Compact Array, which is a 6-antenna telescope near Narrabri in New South Wales. And now we're just opening the ASCAP telescope. And those are all run by CSIRO. And we run them as what we call national facilities. So they're available to anybody in the world to apply for time on them, and time's allocated on a merit basis. So the better the science, the more likely you are to get time. You can also nowadays buy time on them, and that's what the Breakthrough Listen team have done. So I don't know if you've heard of Breakthrough Listen. Breakthrough is an organization run by Yuri Milner, tech billionaire from the US, and he's interested in looking for extraterrestrials. So he has funded time on Parkes and a couple of other telescopes worldwide to do SETI. And so he's bought 25% of the time on Parkes, but mostly it's available on merit. So our newest observatory is the Murchison Radio Astronomy Observatory, the MRO. And this is our observatory in Western Australia, outside Geraldton. We set it up for the SKA, but also to be the best radio astronomy observatory in the world for whatever telescopes we or other countries would like to build there. So at the moment, there are 2 main telescopes there, ASCAP, which I talked about, with 36 antennas, and the MWA, which I also mentioned, the Murchison Wide Field Array, these kind of spider ones here. And ASCAP is a particularly interesting telescope because it uses a new kind of camera called a phased array feed. So typically radio telescopes only kind of take 1 pixel at a time, or maybe if you're lucky, kind of 15 pixels if you've got a multi-beam telescope. ASCAP has these new radio cameras on the front, which allow us to see 30 square degrees of the sky at one time, which is 30 times the size of the full moon. So that means we can take, really big pictures of the sky. So ASCAP is just in commissioning at the moment. In fact, 3 papers were released yesterday with early science from ASCAP, but it's going to be a real game changer for astronomy. And in fact, I've had astronomers say, once you've used ASCAP, you'll never go back to having to kind of point slowly across at all your pictures, because you can actually take a picture with a camera in the same way that optical astronomers have been able to do for decades. So the Murchison Radio Astronomy Observatory, 350 kilometres, as I say, outside Geraldton. It's an area about the size of the Netherlands with a population of 120. So you can see why it's quiet, right? So you can see the radio frequency measurement, radio interference measurement on the top for the Murchison compared with Sydney, right? We used to have radio telescopes in Sydney, but really it's not tenable anymore. You wouldn't be able to see anything at all. So it's nice and quiet. In fact, it's just fantastic. So quiet that at nighttime, you can see on the left-hand side, this is an image taken by ASCAP, shows you the frequency band. It's really quiet. During the day, probably somebody working for us on our site comes and leaves their mobile phone on. There's no signal over there, so there's no benefit to be gained by putting your mobile phone on. But you can see the phone, and you can see the mobile phone tower trying to talk to it from 150 kilometers away. So that's how quiet it is. 1 mobile phone and we can see it. So what we have is we have a radio quiet zone. So mostly you rely on the fact that there's nobody there, broadly, for it to be quiet. But we also are protected by a radio quiet zone managed by the Australia Communications and Media Authority, which gives us priority for radio astronomy work within an inner zone of 70 kilometres. So if anybody wants to do things that will give off radio waves, so needs a license for anything or wants to set up an electric fence or whatever, they have to come and talk to us first. And we can talk to them about minimising the impact on radio astronomy in the area. And then there are other zones right out to a coordination zone, even 260 kilometres from the site, so that we can work to really keep that pristine, best radio quiet environment in the world. So here we go. So this is just a video that shows you what it's like at site. So you've seen some still images of site, but this will give you a better idea. And it's really a beautiful place to go, but don't go. So we do not welcome visitors. go to Geraldton, it's lovely there. They've got a great museum. But you can't come to the MRO, unlike Parkes, where you can go, or even the compact array at Narrabri. So the ASCAP, our Pathfinder telescope, some of you might have seen stories about fast radio bursts a couple of weeks ago. So ASCAP, we published a paper in Nature 2 weeks ago. ASCAP has found 20 fast radio bursts using its really wide field of view. And fast radio bursts are really, really short, really, really bright signals from the sky somewhere, and we don't know what they are or what causes them. But there's only around 20 had been found from any telescope anywhere in the world, most of which had come from Parkes. Now we found 20 more using ASCAP because of that great field of view. In fact, when we designed ASCAP and when we were building it, fast radio bursts weren't even a thing. So that just demonstrates your telescopes, you never know what they're going to do. So this is the MRO control building. And the important thing about the control building, you can see, is that because it's on site and it's got an enormous amount of digital signal processing capability inside, it has to be really well shielded. So you can see we have double doors that you have to go through, and all the fibers that go into it have to go through special filters and things, so that the electronics inside don't interfere with the telescope. And then this is not actually any longer like Australia's largest lithium-ion battery now that Elon's come along in South Australia. But at the time we built it, we have what we believe is the first observatory in the world that can be run entirely off solar power. But of course, we had to make a solar power and battery station, which was also very radio quiet. And so we worked with the solar power suppliers and the battery suppliers in order to do that. And that's of interest, for example, to other, say, defense users who are talking to us, because they're also interested in radio quiet solar stations. So you can see, so you saw ASCAP, the Murchison Wide Field Array there, some test SKA antennas, and then pictures of what SKA will be like. So at the moment, we have ASCAP and we have the MWA. We'll start building SKA on site probably in about 2 years' time. And then it will be complete 6 or 7 years after that. We'll probably start taking data a little before it's complete. But the one part of the telescope that you didn't see is the supercomputer. And I say the supercomputer is part of the telescope because these new telescopes, the MWA, ASCAP, but in particular SKA, but even ASCAP, you absolutely need a supercomputer. So astronomers have traditionally been terrible with their data. I think it's fair to say. So what they would do is they would go up, have time on a telescope, they'd record their data onto tape, they'd put it on a shelf for 3 years, then they'd think about processing it, eventually they'd write a paper. We can't do that anymore with ASCAP and the SKA because the data rates are so enormous that we cannot store the raw data. So what we have to do is we have to move it to a supercomputer, which has to process the data in real time. And then it's available to astronomers to reprocess that initially processed data if necessary. But this raw data, we can't keep anymore because the data rates are too large. So I'll give you an example of what the data rates, and these are the data rates not into the telescope, not into the supercomputer, but out of the supercomputer into the archive. So ALMA, which is a high-frequency radio telescope in Chile, that has about a petabyte a year of science data products. That's a telescope that's going now, big international telescope. LSST, the Large Synoptic Survey Telescope, which is an optical telescope for surveys, will have about 4 to 5 petabytes a year. The Large Hadron Collider, CERN's particle collider, when it first started was storing around 15 to 20 petabytes a year. There's going to be a high luminosity version of the LHC, and the science data products from that will be about 400 petabytes a year, which is finally of a scale about what we expect the SKA to be. Yeah, so we expect SKA just in its processed form to be 130 petabytes a year, but once you have enough reprocessed data and a full discovery archive so the astronomers can go in, we expect there'll be about 700 petabytes a year, and that will be distributed internationally. So it's a big data challenge. And that's not the data that we start with, of course. That's the data that we more or less end up with once we've processed everything and once we've cut off a lot of what we don't need. So finally, then, this is just a video that describes the kind of data chain to you and where we're up to. So signals come down, they hit the dishes or the antennas, yeah, and then they're transferred. So they hit the, we detect them using receivers, they're digitized and transferred to digital signal processing facilities in what's our central processor facility. So each telescope will have a building like the one you saw with the double doors, very carefully radio quiet shielded. And in the central signal processing facility are the DSP activities, and they're a mix of GPU and FPGA processors. GPU more for what we call time domain astronomy. So where we essentially add together all the data and try and measure things that are really fast. And we need to be able to measure changes in those millisecond pulsars, all those fast radio bursts that only last like a millisecond, and we have to be able to detect them. And then there are FPGA correlators and beamformers. So they process the data from the antennas. And what we do is we take what we call baselines. So it's between each two antennas. So there's 130,000 antennas in the SKA low. And so we have to multiply the signal that we get between every two of those 130,000 antennas. And then we break it down into up to 68,000 frequency bands. And then that results in an image. Yeah, so in what we call visibilities that the astronomers can then use. And then once that data has been processed using the DSP, it's sent to our science data processor centers, our supercomputing centers. In Australia, it will be the Pawsey Center. In Perth, in South Africa, they're building a supercomputing center in Cape Town in order to manage this. And there with we have two supercomputers which do the initial processing. And the calculation is that we need altogether up to about 250 petaflops of processing to be able to manage these 8 billion channels of data that come out of the telescope and have been processed initially using the DSP. And then that data, once it's been processed, will be distributed around the world to what are called regional centers. Because SKA does not have enough money as a project as a whole to provide all the computing, the storage, the user support that the astronomers are going to be able to need to use this data. Obviously, with this level of data, they can't. The cat coming nice. With this level of data, the astronomers absolutely can't download this anymore to their desktops and try and kind of process it on their laptop, which they still do. What they have to do is they will have to log into someone's computer cluster or supercomputer, and they will have to access the data where it is and process it in situ. So it's more like a cloud, I guess. And so what will happen is the data will be distributed around to regional centers worldwide. And there'll be at least one in Australia, possibly one on the East Coast, possibly one on the West Coast. And those will be where the astronomers go to get the data, to get the user support, to get the processing that they need in order to make science from this. And this is a real paradigm shift that we're just in the middle of now with ASCAP and the MWA, building that supercomputing facility for the first time really into our telescopes in a way that we've never had to do before. So it's a real change for us. Those are the credits. And then finally, one thing that I didn't mention, in order to build ASCAP and the SKA and MWA at the Murchison Radio Astronomy Observatory, we have to work very closely with the local traditional owners of the land. So we have an Indigenous land use agreement. We have one now, and we're negotiating a new one for SKA, which allow us to work with the Wadjuri Yamaji, who are the local Indigenous owners. And so that's a very important relationship that we have. And we, in particular, acknowledge the Wadjuri Yamaji as the traditional owners of the observatory site, and we are extremely grateful to them for letting us use their land. So I'm happy to take any questions.
Any questions?
Hi, thank you very much. I noticed with the MRO, it didn't seem like there was any kind of clear pattern as to where you'd situated the satellites on the site.
The antenna, yes.
The antenna, sorry. So some were more bunched up, some were further separated. Could you give some insight into how you decide where exactly to put them?
Yeah, so what you need is a distribution of antennas that covers, that makes you get a nice smooth image in what we call the UV plane, in the Fourier transform of the interferometry. And so the way you usually get that is you have a core which has antennas close to each other, and that gives you kind of sensitivity near the middle. And then you have spiral arms. And in SKA's case, there'll be 3 spiral arms of antennas going out from the middle core. The middle core will be around 1 kilometer in size. And the 3 spiral arms go out. Why are they in spiral arms? Well, you could have them more randomly distributed, but that's extremely expensive in terms of infrastructure because you need to put kind of roads and fiber and things to each of the antennas. So you have 3 spiral arms, and that sets you up with a really nice smooth image in the UV plane. So you get a nice picture when you do the interferometry. And so, but you can't have them, you have to have them kind of reasonably randomly distributed. Yeah, you can't have too much of a regular pattern.
Any other questions?
Yeah. Hi. So first and foremost, I don't work for cloud sales, but I'm kind of curious in the construction of the data center that you're talking about, and in some of the choices that you made around that, whether or not you did actually look at what are now public cloud providers for some of the second order data processing stuff. Just because I know like NASA JPL had kind of a similar processing challenge and basically opted for a solution of they had a lot of dedicated hardware that was doing stuff kind of similar to your GPU and FPGA array on site to cut it down, and then all of their second order processing in a public cloud, and found that ultimately saved them a lot of money that they could spend on like other more sciencey hardware.
So we're exploring the possibilities of cloud processing. We've been working with Amazon. Certainly. So when I talk about as having a supercomputer, look, I think for that pipeline processing, right, where it's really high I/O, and we found that the I/O has been typically the most difficult bit to do with the cloud. It's really high I/O, and you really need like kind of control of the computing. We found that for that first pipeline processing, really, we're probably going to need a supercomputer for quite some time. But for the regional centers, the second kind of tier processing that the astronomers themselves do, or that the survey teams will do, absolutely. I think at the moment we're envisaging there'll probably be a supercomputer to start with, but there might be a mix of supercomputer and cloud, and at some point there might be only cloud. Yeah. So yeah, we're certainly exploring that. Yeah.
It's probably maybe a bit early days, but how does science get the targets get chosen? Who gets to choose where you're looking?
Yeah, so this is a reasonably well established model for astronomy generally, but in particular for radio astronomy. So you have what's called a time allocation committee. So every 6 months or so, you open up a call, people put in proposals for what they want to do. You have a time allocation committee that represents all the different kinds of astronomy that people might want to do. And they assess the proposals in the same way that they might be assessed for an ARC grant or whatever. And they're listed then in order of scientific priority. And then people go away and try and allocate time on the telescope for them. And then there's a line kind of below which there's no time. Now, SKA is going to be a little different, and ASCAP is already a little different to typical radio telescopes, because SKA will have such fast survey speed and ASCAP has such fast survey speed. What we're going to have is quite large collaborations of astronomers doing surveys that need kind of thousands of hours of telescope time. So ASCAP has survey science teams which have been decided for almost a decade now. 10 priority survey science teams, which will do, for example, looking for images of galaxies, looking for 1 million galaxies, or looking for the spectra of 70,000 galaxies. or looking at high time resolution work. And so most of the time on SKA will be given over to those kind of large collaborations. Then there'll be time for individual astronomers or small groups to apply for. SKA is unusual in radio astronomy because most of the time will be set aside for the SKA member countries. So traditionally in radio astronomy, the telescopes have been available for anybody to use. The VLA, it's in America, but if you want to apply for time on it, you're absolutely welcome to do so. Same with the Parkes telescope. The SKA, the vast majority of time, probably 95%, will only be available to astronomers from countries that have bought in. And then there'll be a very small amount of time which is available to anybody in the world.
Any other questions?
So what usually happens is that there is a proprietary period. So the data is available to the team who took the data for a year. That certainly is a proprietary period of a year on CSIRO's radio telescopes. And then it's completely available, completely openly available to anybody after that.
You said that the observation speed was going to be on the order of 100 times faster than the VLA.
Yes.
What about the sensitivity and resolution?
So those stats were in the, I have to go back a bit. In the slide. So sensitive, both SKA telescopes are being, if we can make this go. Okay, here we go. Yeah, so both SKA telescopes are really optimized for survey speed, right? So when you look at citations of astronomy papers, it's those massive surveys really that get cited and where take the community forward really. And so both low and mid are optimized to make them much faster in survey speed than previous radio telescopes. So the sensitivity is good. So you can see with SKA1 mid, it's 5 times more sensitive than Jansky VLA. And SKA1 low is 8 times more sensitive than low far. Yeah, but it's really in that survey speed and in being able to see things across the whole sky that you get this massive increase in capability.
What is the cadence? How fast can you do the whole sky? Visible sky, obviously.
I don't know that off the top of my head.
Like a week, a month?
Yeah, it's that kind of scale. Yes, that's right. I mean, it depends how long you want to look at anyone. So how deep you want to go in any one area of the sky. So you can do, you can do a sort of shallow survey, obviously, much more quickly than you can do a deep survey. The ASCAP science surveys, we expect, to take a couple of years in order to get that kind of depth. So between each survey. Yeah.
So I assume you can only look at the southern hemisphere sky, right?
Yeah. Yes.
So
I mean,
did that play into the equation where to build it? Is one expected to be more interesting than the other, or?
So you will have noticed that both SKA telescopes are in the southern hemisphere, and that's because from the southern hemisphere you can see the galactic center for much more of the time than you can from the northern hemisphere. So we kind of point towards the galactic center, and so almost all, not quite all, but almost all telescopes that are built at the moment are built in the south. So ALMA is in Chile. The large optical telescopes are being built in South America because you get that view of the galactic center that you don't get from the north. You do also need some telescopes in the north, obviously.
What else? Okay, one more.
This is not a science question. I'm just curious, you mentioned, I think it was Parkes, and you were saying that 25% of the time is available for purchase, which, sounds great on one hand, but I'm curious whether, so that's a way for you to have a source of income, but I'm curious whether, 1 year later after you launching that or whatever, did your government funding reduce by 25%? Like, did they notice, or how did that come about?
So it was kind of the other way around, in fact. We needed to find funding to allow us to operate ASCAP as well. So we've got this new shiny telescope, which is a long way from anywhere and costs quite a lot of money to operate. I mean, it's 36 antennas, it's, and it's 350 kilometers from where people sort of live during the week. So So we needed to manage our budget to allow us to continue to operate the existing telescopes, but also operate the new telescope. And so this was the model we came up with. Actually, Breakthrough Listen came to us to say, could they buy time on parks? But we agreed that up to 50% of time on parks and the compact array is available for sale. And 25% of time, in fact, on ASCAP. So if you think of something fun you would like to do, and you can get Google to give you some money. But what that allows us to do is it means that much of the direct costs of running the telescope, so the sort of salaries of the people and the electricity, are covered by selling time. And that allows us to then make the rest of the time available as national facility time. So in parks, still most of the time is available in a way that it wouldn't have been possible if we'd had to maybe massively reduce the time availability because we couldn't afford to run parks anymore in the same way that we have been in the past. So that's how that came. So in fact, our government money has been more or less going flat or going up a little bit. So it wasn't about reduction in funds, more about trying to do more with the same money.
Well, on that happy note, we're out of time. So let's all thank Sarah for an absolutely fascinating talk.